Hello, everybody. This is Mrs. Wild from your WCA physics class, Physics B. We are looking here at Unit 3, Lesson 3 on Coulomb's Law. This is a fairly long lesson, so it might be a little bit longer of a video than normal. Hopefully I can keep it kind of like relatively manageable and short. Our keywords are Coulomb's law, electrostatic force, negative charge, and positive charge. And yeah, this one's kind of filled up with math, you guys. So pay careful attention. So this first section just talks about how Coulomb developed the law, the rule, through experimentation. So I'll kind of let you read through that. But Coulomb's law basically tells us how much um, force there is between two charges. So when you look at two charged objects, how much force is pulling those charges together or pushing them apart? So if you remember from my last video, I used a kind of charged up piece of tape to pick up some little pieces of paper, and it was a pretty weak force. It was really difficult to pick up a tiny little piece of paper, and I just got one. So that's a fairly weak electrostatic force. On the other hand, if you think of like an electromagnet, for example, that's a pretty strong, that's a magnetic force versus electrostatic force, but it's a much stronger force. Or even just thinking of in terms of like a sock stuck to your shirt after you take it out of the dryer, it sometimes has a fairly strong static cling. So it's also a decent size force. So we use the Coulomb's law to mathematically calculate how much force there is. And it is written like this. The electrostatic force, which is F sub E, is little k, which is Coulomb's constant, which is written here, times the first charge times the second charge divided by the distance between them squared. And I'm hoping maybe this looks a little familiar because this is very similar to our universal law of gravitation that you just learned about at the end of first semester. So you might remember this formula here, very, very similar, almost identical, but you just have the strength of the charges versus instead of mass, and the universal constants are different, or the constants are different here, right? So that's kind of what makes it different. Obviously talking about something completely different, but we can use gravity as kind of analogy when we talk about electrostatic forces. So in this case, again, our K is Coulomb's constant, and it has a fairly funky unit, kilogram meters cubed, um, divided by s to the fourth a squared. I don't even like that unit. You can simplify Coulomb's constant. Let's just, here we go. 2 meter, oopsies, 2 meters square, meters squared per Coulomb squared. But we haven't yet talked about what a Coulomb is. Coulomb was a person, but we also have a unit that is named after Coulomb. And I'm just skipping that for a moment. I'll come back to it. But this is what a Coulomb of charge is. So let's see. Protons have a charge of 1. Basically, protons and electrons have the same charge. Protons are positively charged and electrons are negatively charged. I'll tickle in my throat here. And 1 electron has the charge of 1.602 times 10 to the negative 19 coulombs. So a coulomb is a larger unit to make it easier for us to be able to to look at stuff at a kind of a macro level, because electrons are really, really tiny. So if we just use the charges of individual electrons or tried to count individual electrons, it would be kind of ridiculous. So the number of electrons that are found in a single Coulomb, I don't think that's ever given in the unit, number of electrons per Coulomb is 6.24 times 10 to the 18. That's electrons per Coulomb of charge, per Coulomb. So rather than focusing on one electron and its charge, we focus on the number of coulombs of charge because we've got so many electrons, if that makes sense, you guys. All right, so let's move on to some questions here. Oh, so I forgot actually. My bad. I was going to go back and talk about the top of this part here. So here's our formula, but then they also bring in this little guy right here, and I know I like him because honestly, in every other physics book I've ever taught from, or even in classes, like my son just took a electronics class in the college, they don't use that. But this is basically telling us that, hey, force is a vector. So we have to be concerned with both the quantity of the force, the magnitude of the force, and its direction. And so this little r with the symbol at the top there, which I'm really not very familiar with, is called a vector unit or a unit vector. And it just tells us direction. So in this case, it's going to tell us whether it's being attracted or repelled, basically. And its magnitude is 1, so it doesn't add or contribute any sort of value as far as magnitude to your problem. It's not going to change the math. This will still be how you come up with a magnitude, and then it's just going to tell you the sign, negative or positive, okay? So honestly, I'm not really concerned too much about that. All right. So moving on to, we're on page 8 here. Again, it's giving you the formula for Coulomb's law. Just going to ignore that little r, you guys. I'm seriously going to. And it's giving you the value for the Coulomb constant. And it says that if you look at the charges, charges can be positive or charges can be negative. So that's where it kind of differs from looking at gravity. Gravity is always going to be a pulling force, right? Whereas the electrostatic force can be repulsive or attractive. It can be either or. And if it says both of the charges are positive or both are negative, then when you multiply two negatives together or two positives together, you end up with a positive attractive force, right? The math rules in that case. If they have opposite signs, then they will always be negative. So does that kind of make sense? So if they're both the same, this is kind of cool if you ask me. If they're both positive or both negative, then you get repulsive. So if they have the same charge, they repel. If they're opposite, then they attract. We kind of knew that already, like practically speaking, but it also works mathematically because if you put in here, oopsies, up two positives, then your force is going to be positive. Or two negatives, then your force will be positive. So the positive force means repulsion, negative force means attraction, okay? Kind of, I don't know, in some ways it's counterintuitive that way, but it's also makes lots of sense when you think about experiential, like when you think about, have we ever had an experience where opposites attract and likes repel? Now it says it's easy to determine what happens to two charges. You put two charges together, you just have to look at their signs and their magnitudes to figure out what's going to happen. But what if you've got more than two? What do we do with that? We have multiple charges. So this is where we have to come into, it says this, the principle of superposition comes into play. You have to figure out how each is going to affect the other. So let's see here. If we had a line, this is the first example, and it says, you have a line, and it says you have a -3 charge here, a -3 charge here, and right smack dab in the middle, you've got a +3 charge. So it's going to be attracted to this with the exact same magnitude as it's going to be attracted to that. So it doesn't go anywhere. It's kind of balanced in the middle, right? And then let's look at this more complicated example. In this more complicated example here, you have in the middle a +3 charge. Then it says to the right 2 centimeters away is a -4 charge. And 1 centimeter away to the left is a -1 charge. What is the net charge acting on this guy here? So it says the net force is going to be 0. There's no net force. And I was looking at this going, okay, how do you determine that? So you have to look at Coulomb's law to determine that. And we're first going to look at the force between these two. And then we'll look at the force between these two, okay? So let's go back and let's see here. It lets me erase. Nope, it's pretty naughty that way. It doesn't have a back button. Oh, schnookers. I'm going to rewrite that, okay? So we've got our +3, and then 2 away we've got -4, and then 1 away we've got -1. Okay, so we'll look at these two first. So I'm just going to write part of Coulomb's law. So K, I'm not even going to worry about K, because K is going to stay the same regardless, so we don't even have to deal with K. So we're just going to do charge 1 is +3, charge 2 is -1, the distance between them is 1 squared. So when I figure that out, +3 times -1 is -3, and 1 squared is 1, so -3 divided by 1. The charge between these two is -3, okay? Then let's do the charge between these two, okay? So again, leave K alone, we don't need it. But our first charge is +3. Second charge is -4. The distance between them is 2 squared. So 3 times 4 is 12, and it's a -12, divided by 4, and that equals -3. So -3 pulls in one direction and -3 in the other direction, and that means it's getting pulled equally in both directions, so the net charge on it is 0. So if you don't know, that's kind of how you break it down. You kind of look at the charges between these two first, and between these two, and then between these two. All right, so I'm gonna go ahead and clear that off. And let's see, this last section I'm not gonna go through because this is having you use one of the sims, the FET sims, which we have used for portfolios before, to be able to play with it a little bit. You're going to play with different charges, different distances between them, and kind of look at the net charges between the two. You know, what is the charge between, or the force, excuse me, between the two charges. You can kind of manipulate and play with that on FET. And I would really encourage you to do so because it does help you kind of really cement those ideas. So that's it for this lesson. I hope it wasn't too long. Have a great day, everybody, and we'll see you in the next one.